There's a balance there because I'm pretty sure, like, at some point you're going to be miserable from eating all the butter.
Well, this is true. This is why we have to balance it out. You know, you have an entire stick of butter with an entire pint of, I don't know, vegetables, right?
A pint of, I'm like waiting for Ben and Jerry's. Okay, so I think we probably could have squeezed last class and this class together, but if we'd done that, we wouldn't have had enough time to practice last time. And anyway, so this will probably take 20 minutes-ish, maybe a little more. And then we'll just do some Chapter 7 practice problems, okay? So Chapter 12 homework due tomorrow night. The practice exams are not until Sunday night because the exam is on Monday. But since Friday's the review, I would highly recommend at least like the Chapter 7 one. You should be able to at least do it once and come in with some questions. Okay? All right. Phase diagrams. So I think instead of explaining it to you in detail beforehand, I'm going to give you a brief overview, and then we're going to like have these questions that kind of walk you through how to read a phase diagram. And then we will recap all of the key points at the end. So, brief overview is a phase diagram, shows you how a compound, water in this example, will behave based on its temperature and pressure. And it specifically tells you about phase changes. So the lines that are part of the diagram, not these ones here, let me show you the other one. Nice clean, not the dotted lines on these ones, but just the regular straight lines. I feel like I'm in a weird space. The solid lines, I'm like, straight lines? What is that? The solid lines represent phase changes, okay? So those solid lines represent the difference between the solid and the liquid, or this one between the liquid and the gas. So if you ever cross over a line, that's a phase change occurring, okay? So this one would be melting, that would be freezing in that direction. This would be boiling or evaporation. This one would be condensation. We've maybe said this already. Solid to gas is sublimation. Gas to solid is called deposition. So anytime you're either changing temperature, so a change in temperature would be going this direction, a change in pressure would be going this direction. If you cross over one of those lines, then a phase change will occur. The phases will always be solid, liquid, gas. They're just kind of all interconnected there, but they always are in that order. So this block over here will be solid, this block will be liquid, this block will be gas. Even if they're not labeled, you can assume that. Okay? All right, so let's just start with kind of trying to read some of these diagrams with a couple basic questions. So we're going to make it small just so we can see everything all at once. So I want you to go to that point. Okay? So take 3 minutes on your own with your neighbor, whatever, and look at the two phase diagrams. Read the diagram to tell you the physical state at these different conditions. I feel like there's a couple of confused faces.
Well, I'm just looking at the one for water, and
Yeah.
it like perfectly meets on the line. But for
Okay.
for 0 Celsius.
Yeah, talk to Lily and see what you think. That's a good confusion look then.
Yeah.
You're actually thinking, not just like, what did she tell us to do?
Please believe it's much more liquid.
See, I haven't read that book because we covered this section. Briefly, very briefly. But there's a lot of diagrams. I feel like it's supposed to be some gas. Water solid.
It's gonna have this and these both of them are pretty similar. You think that's good?
Same as the
Yeah, I agree. There's that together. There's. No, one is a big regular, one is a. Okay.
Thank you.
These are beans.
Okay, so all of these conditions are at 1 atmosphere, which means that it should be a horizontal line across the plot. So one important note, you know that pressure is the y-axis here. So if everything's at 1 atmosphere, you're just talking along that dotted line that's shown in the water one. They don't extend the dotted line here along that dotted line for the CO2, okay? Then you want to look at the temperatures. So first one was 25 degrees C. So water is a liquid at that state. Shouldn't be surprising. That's what we're used to. CO2 is a gas at that state. So wherever the pressure and temperature are, you look at what phase that's in. Okay, so it's in the gas phase here. It's in the liquid phase there. Now the scale on this is different because the properties of CO2 are so different that it wouldn't be a good representation for us to use this scale of pressure and temperature. So obviously they're, you know, they look slightly different than each other. You still get the right answer though. All right, so B, which is 0 degrees Celsius and 1 atmosphere of pressure, CO2 is still a gas. Okay, so even at the freezing point of water, CO2 will still be a gas. Good, I think we're good with that. We've experienced that. It's cold outside at some point, there's still gaseous carbon dioxide. You're not making a solid as it comes out of your breath. For water, you're actually on that line between a solid and a liquid. So at 0 degrees C and 1 atmosphere of pressure, both solid and liquid are present. So solid and liquid. Here it was a gas, here it was a gas, this was a liquid. So if you're on a line, both phases exist. You have to cross to one side or the other for the phase change to actually fully occur. Yep.
What does it mean by critical point?
We haven't gotten to that yet.
Yeah, Louise.
Actually, I'll answer that. Let me just finish C. So then C is negative 100 and 1 atmosphere of pressure. That's not something we have familiarity with because we're not ever that low in temperature. But you can imagine that ice would still be ice at that temperature. It would still be solid. That at that point, CO2 is actually solid as well. Okay, so since Lily asked, we'll talk about it. Critical point is the point where you start to ionize things. So it's not really, you can't really talk about what phase it is because now you're pulling off electrons. So that's why you don't have a clear-cut phase point. Same thing with a supercritical fluid, I believe, is that you now have, I feel like I should get a better definition of that, but I think you're ionizing the gas at that point. And then the triple point is not something that we're particularly familiar with because the conditions that they happen at are so different than normal life conditions. But if you were to take a sample of water, whatever phase it was in, stick it in an experimental device and then pump out the air surrounding it, so create a vacuum until you got to relatively low pressures, not no air molecules, but a very small amount of air molecules, then at that pressure, that really low pressure, and about the normal freezing point, so slightly higher, but about the normal freezing point, you would actually see solid, liquid, and gas all at the same time. And if you increase the temperature, you would get the liquid phase. No, sorry, the gas phase. I was like, yeah. The gas phase, if you increased the temperature. If you decrease the temperature, you would get the solid phase. And if you increase the pressure, you would get the liquid phase. I feel like there was something else I was going to say about that. No. Okay, next segment. Okay, you've got, I could tell this morning, I was like, oh, I must have written this during COVID. Or that time when I was getting meat delivered from, I don't know, some yummy meat. Okay, so they're shipping stuff, something perishable. It's at 1 atmosphere of pressure. It's just sitting in a FedEx truck. They stuck solid CO2 in there at a negative 100 degrees C temp initially, and then we want to know what happens. So I want you guys to draw me a line on your diagram of the CO2 to represent the process that would occur as the FedEx truck drove into warm conditions. Do you want me to leave the question showing or the diagram? The question, okay. The reason I don't have a better definition for you is because it literally is just like where the gas and liquid phase merge into a single phase, and it kind of has properties of both. Like,
So it's like looking at like a really large quantity of gas, how it interacts kind of like a fluid.
no,
No.
unless it was at higher pressures.
Okay.
Yeah. Are you pulling this from some other class, trying to make some analogy?
Yes.
Mm.
So meteorology would look at the atmosphere as like a fluid.
Oh, like the dynamics of how it moves and stuff.
Correct.
Yeah, that's not related to this at all.
Okay.
Yeah.
Oh, no, I never got to play with that thought experiment before. Is the box fully sealed? Like,
No, I mean, it's, how could, it's not like,
it's not airtight?
no.
Okay.
It's like a cardboard box
We're not
with
blowing
like,
the box up?
no, like it's a cardboard box with like some insulation. Have you never had something sent
No,
with,
I have.
okay.
I'm just trying to think about.
No, but
Maintaining pressure.
let's say you had a FedEx truck full of that stuff, you could easily get asphyxiated if you stood in the truck and had the door closed.
Yeah, this is something you gotta be careful about.
Yeah.
I was thinking about like dry ice rockets.
Yeah. No, it's not. It's not a closed. That would be very stupid.
It'd be very messy. But also, people tend to be that stupid in real life.
True. Okay, so apparently I had already drawn the dashed line from earlier because I was showing you where the 1 atmosphere line was, but that was the line you were supposed to draw, is basically you're starting at C and you're driving and it's warming up and you're going, you know, up to room temperature-ish. Okay, so in that process, you cross over that black line, the solid line there. So you're going from a solid to a gas phase. You get sublimation occurring simply because that increase in temperature. Okay, last part, we're gonna look at the 2 lines, well, the lines on both diagrams that separate the liquid and solid phase. So we're talking about these ones here. So you should notice pretty quick that they're different. Water has a negative slope when it's pointed this way. It's the math definition, right? Negative slope, whereas CO2 has a positive slope. It's very slightly positive, but it is positive, okay? So we're gonna do a couple little problems that will tell us something about what that means or what it implies about the substance, okay? So these 2 questions here, work through those. So in both of these, we're increasing pressure, so you should be holding the x-axis constant and going up in y and seeing how it changes. All right, so for the water, if you start with ice and you apply a pressure. Now, when we talk about applying a pressure, sometimes we mean, and I need to talk about this in a second, we do need to talk about atmospheric pressure. Versus an applied pressure versus like compression of a gas. Okay, so these are all ways that we can apply a pressure. It doesn't matter how that pressure gets applied. It could be a physical force. It could be because of the molecules in the atmosphere that are pushing on it. It could be because we take something and we scrunch the container around it down. So let's just think of like a piece of ice and a butter knife, okay? You don't even push very hard. You just like gently push on the knife on the ice. It's going to turn some of that ice into water, okay? So that's what happens when you are at 1 atmosphere pressure. You increase the pressure. Do we have any hockey people in here? No? I don't know where they all went. I had them last semester. That's how ice skating works. You have a blade, you push it on the ice, it converts it into a very thin layer of water, and then you glide on the water. This is also why, no, I'm not there yet. We'll get to that in a second. Okay, CO2, let's look at the opposite, what happens with CO2. I actually want to look at this one. Let's start with a solid, just like we did with the ice. Okay, so it doesn't matter what the conditions are. Let's say it's a high pressure though, relatively low temperatures still, but we apply a pressure to the solid, nothing happens. It just stays solid, okay? So if you have something, whatever that something is, think of like a cotton ball or a marshmallow, okay? And you squash it, it's going to get more and more dense, right? Like that's what we're familiar with. If you have a marshmallow is a bad idea because I'm thinking of a piece of bread. So you've got a piece of bread and it's like squishy. Maybe this is because my kids do this. But then you like squash it and now it's this tiny little nasty dense ball of dough basically. Okay. So this is what we're talking about. We're squashing something. So it should seem a little bit weird that if you squash ice, you make water. Okay. That is unusual. This is not a typical response of compounds. Ice is unique in this. What that's really telling us is that the water is the more dense phase. That's okay. And that's unusual. So the CO2 is actually more typical of other substances in bread, if we want to use that example, marshmallow, whatever. Those we're squashing air out of, so there's not actually a phase change happening. But most substances are going to shift to the solid phase as their more dense phase. And water is unique in that. So this comes from, maybe I should try to pull up a picture of this, but this comes from the hydrogen bonding. Was that somebody in here that asked about that? The hydrogen bond? Okay, let's see.
I was wondering, you said like compressing the liquid which turned into a solid. Is that like a non-Newtonian fluid that's like compressing it into a solid?
No, it's not actually. That was not a very complete answer. That's a totally different thing though. But it's fascinating, and I'm thinking of cornstarch and stuff like that. Yeah. This is just simply because there are empty spots it's probably the best we're going to do. So in ice, it forms those hydrogen bonding intermolecular forces, and it wants to form as many of those as possible. And so in order to do that, it forms an interaction with the oxygen with another water molecule, and then the hydrogens with the oxygen side of 2 other molecules. And what you get is this very structured, ordered crystal in the ice where the molecules are not particularly close to each other. So in a lot of crystalline structures, like we've seen this before, but that doesn't, okay, there, that's a better picture of it. So in sodium chloride, the atoms get really, really close to each other and they're still very ordered and structured. In water, the way that they have the best structure is by separating themselves out. They can't get super close because they're trying to maintain this like hexagon shape with the other atoms. So what you end up with is these like tubes throughout ice that are just empty space. So when you start to compress them, you can get rid of some of that empty space, and the water molecules still interact, but they're also free to move around and form those interactions with neighboring molecules. And so that is why ice floats, why it's less dense than water is. Oh, okay. So summary point, and I have this written down there, is that if you have a phase diagram that has a negative slope, it's telling you that the solid phase is less dense. Or you would see the solid floating on the liquid of that substance. But like if you froze oil, okay, you had an oil ice cube, and you try to put it on the liquid oil, I'm talking like olive oil, we could go do this, right? It's not gonna float, it's gonna sink to the bottom. Okay, that's it. I don't have a good answer about why non-Newtonian fluids are the way they are. I don't think it has anything to do with their density necessarily, but I don't know a lot about them.
Okay, have you read about the non-Newtonian fluid speed bumps they're putting in Europe?
In where?
In Europe.
Swimming pools? Is that what you just said?
Like speed bumps.
Speed bumps.
So like if you hit it, if you're going fast, it's a solid, but if you're going slow.
Is that a real thing or is that a TikTok fake
No,
thing?
I looked into it because I was like, this seems.
That's so cool.
Yeah, it's like it's an experiment that they're doing.
That's really cool because then you wouldn't end up, you know,
Losing the bottom of your car.
right, if you're going a reasonable speed. You don't have to slow down to 10
Exactly.
in a 25, but if you're going 40 in a 25.
Then it'll like
Yeah.
really hit you hard.
Okay. I like it. I'm gonna look that up while you guys are doing this problem. All right.
But if it isn't a thing, then it should be because that's really cool.
Did you hear about it on TikTok though?
No, I don't have to.
Okay. Oh, right. We've had that discussion. Okay. I want you guys to do a Hess's Law problem for practice to remind you some of the things we did in chapter 7. And then maybe we'll also do one with delta H's of formation. So some of this you can do by just looking at it, like just start and try to make some guesses, but certainly write down all of the equations. But that's the unknown. That's when you're trying to find the delta H for, and these are your known quantities.
Do we use all of them for this?
Yes. I can't imagine giving you ones where you don't need all of them and also where you don't need any others. So, yeah. Now I'm going to look up about the speed bumps because it's fascinating. International Research Journal of Engineering. I would call that a reliable source. Non-Newtonian fluid speed bump. That is so cool.
Oh, did you also see the really cool one about the brain in Pompeii they found?
No.
About where it turned glass?
Yeah.
So that sounds fake too.
No, but I looked it up in the research journal because I read it on the internet and I was like, there's no freaking way. So I looked it up and there it is. There was a research journal posted on it.
It also looked really cool.
Oh, it's
Like
so
it's
cool.
pretty.
It's like really pretty.
All right, do your work. You're giving us too many things to. But I am gonna send this now to my husband and be like, check this out.
Okay, so you think it's in the universe that like half the principle to get to the font.
Figuring out equation number 3.
Go ahead. Sorry.
sorry. I'll make it come back, I promise.
Bless you.
What happened?
Can you multiply that negative?
Yes. Okay, so don't look if you're doing okay, but if you need some tips. I think, Lily, the phase diagram for something like that must look like it must be a liquid at a very wide range of temperatures, and only when you apply a significant force then is it changing to the solid, right? So it definitely would have, traditional positive slope so that when you applied a force, it would turn into a solid. It's probably something to do with the range at which it's a liquid is very, very wide, and then there's only this small window where pressure applied is going to make it go into a solid, because you would want it to be a liquid in like every instance, even at like low temperatures and stuff. Now I'm going to like try to, you can't look up a phase diagram though for like cornstarch. Like that's not a molecule. When you get more complicated substances, especially mixtures, phase diagrams look very different than this. That may also be part of it. Okay, so when I looked at this initially, I knew that the top one had to be ×2 and that the second one had to be ×4 because I ignored the oxygen for a while. I just looked at C2H2 and I said, okay, that ×2. The oxygen, I didn't want to do anything with because there's oxygen here and here, and then I know it's going to get confusing. So I skipped over oxygen and I went to CO2 and said, okay, I need 4 of those. I got to multiply this by 4. Like, those are my only options to get the right number of the C2H2 and the CO2 in the right place with the right amounts. So I did that first. And when you start with those top 2, you get the 2 things, and then you also get CH4 canceling out, and you've got some water and some oxygen, but they're not the right amounts. So that's how you know you need to do something with the third equation, not to really get what you want, but to get rid of the things you have that are too many, right? Like, I've got 8 oxygens here, but I only want 5. I've got 8 waters here, but I only want 2. So I use the water as my guide just because it seemed easier for some reason. And I said, okay, if I want 2 of them, but I've got 8 over here, that means I need 6 on the opposite side. So how do I get those 6? I take this one and flip it around and multiply it by 6. Honestly, though, the hydrogen, like looking at the hydrogen would have been a good way to do it too. Like, I don't want any hydrogen in my end equation. So how do I get rid of that? I'm going to make sure I have 6 hydrogens on the product side. Okay, so now these guys cancel, and 6 of these cancel and leave 2 there. And these 3 of those cancel and leave you with 5. So I would say this is difficult but doable as far as like what you would see on a test. So now we have to actually add up the numbers. So negative 377.3 times 2 plus negative 890.4 times 4 plus negative 286 times negative 6. So this comes out to be negative 2,600.2 for this equation. So you're figuring out what manipulations, that's what all this is to confirm that you did that right, how to manipulate them, then do it to the delta H's to get your actual answer. Because the test, you don't have to show me any of this. I mean, it's good to do it, obviously, to confirm. But in the end, you're just going to be picking negative 2,600, positive 2,600, negative 850, positive 850. Like, those are going to be your choices, just values. Good? Do another one. Let's do... Okay, so write down the equation here so that I can then make the table bigger. So this is, we're going to use delta H of formation values. So there's a whole table here that you're going to have to use. But this is the equation we're looking for. N2H4 liquid plus 7H2O2, hydrogen peroxide, forming HNO3, nitric acid, and water. Okay? I'll leave that up there for a second, and then I'll just zoom in on this chart so that you guys can look up the actual values. You're using delta H of formation to find the delta H of this equation. see. I don't need any of those down there, so.
How much carbon's in graphite? Is it just like
It's like diamond, it's just a different structure. Yeah, so we were talking about network was that, I can never remember, was that you? Okay. Yeah, so diamond has covalent bonds all throughout, but it's in more of like a spherical shape when they all do their bonds. Graphite is carbon bonds all throughout, but it ends up being a plane. So when you use graphite and you like write with it, it's just like a sheet is coming off. But like to actually break apart the bonds in that sheet, in theory, would be really hard. But it's just a bunch of layers, and so you don't actually end up breaking the layers. They're just lots of tiny little layers.
like that?
Yeah.
Does that mean if you like try to use graphite the wrong orientation for like a pencil, it wouldn't work very well?
I don't think that they're that universally laid down. You know what I mean? They're probably layered, but they're probably also like all wrapped around each other in some weird way. So it probably wouldn't end up mattering.
That makes sense.
Carbon is funny like that because it has so many of these like network solids where it's a bunch of covalent bonds, but then they're all different structures, like coal or, you know, buckyballs.
Yeah.
Yeah. You're like, they're.
Really dangerous kids' toys, you know? Tiny magnets that you can easily ingest and put home.
I don't. Are they?
Oh,
There's 60 carbon atoms all connected. Oh, when I searched that, it came up with buckeye balls, which is like some kind of treat.
candy, yeah.
Yeah.
So peanut butter balls dipped in chocolate. It's peanut butter and powdered sugar. It's delicious.
It really has no usefulness at all. They've been studying it for like 30 years, but it just looks like that. It's a bunch of carbon atoms in a ball shape rather than like, than like a crystal shape. It's not good. It's
They
not
gave
good
it
at all.
such a big long name for something that doesn't really do anything.
Buckminster fullerene, that's because the guy who found it that was like his name. Buckminster. I don't know what, the fullerene I think comes from the shape of it, but.
Okay, I was about to say, like, trying to spell like kindergarten.
Trying to be a kindergartner with.
Oh my gosh.
Buckminster Fullerene. That's the first one I totally be wrong. Middle included.
Bankrupt.
All right, those are the ones we need to use, I think. And make sure you remember it's products minus reactants. Oh. So there's lots of weird sign changes here. So just make sure you use the number as it's written. So N2H4 is positive, leave it positive. The others are negative, leave those negative. that seems oddly large to me, but anybody else get that? Yet? It's okay if you didn't yet. It's okay. I'll double check my work too.
I did the same exact thing and I got negative 4,584, which is probably really wrong.
No, it's, well, that sounded really close. 4,600, 4,000.
484.
Oh my gosh, let me just check my work again. HNO3 times 2, 7, okay, times 2, plus water, okay, negative 285 times 8, and then, so that's the products minus the reactants, N2H4, there's just 1 mole of that, right? Yep. Plus 7 times H2O2. Nope, sorry, I think mine's right. So the coefficients in the balanced equation, that's what's here. You have to multiply those times the delta H of formation for each of these, and then do the products minus all of the reactants. Common thing, like make sure you're actually including all of the reactants before you subtract it. So if that means you need to put parentheses in your calculator, or you need to do it as one and the other and then subtract it.
I think I just calculated.
Well, I always say if you're punching numbers in a calculator on an exam, you always do it twice. You have to get the same answer twice before you believe yourself, for sure. Okay, so we'll just do review stuff on Friday, whatever you guys want. I'll come up with more things, or we'll do stuff from the practice exams. I just realized that we have an exam Monday. Isn't next week's the last week before spring break? So what, we're going to have 2 classes and then go on spring break and you're going to forget everything? Okay, that's...
Just cancel class. What? No. No, I'm kidding.
Did you just say what? No?
Yeah.
And I was like,
No.
I don't know what to do with that though, because it's like we probably, if it was one day, I would totally do that. I don't know. Are people even going to come on Friday anyway? Do people leave
I'll be
early?
here.
Okay.
Yeah.
Okay.
Maybe we could just make it like.
I don't know. I'm going to have to figure out a way to like make it not a cliffhanger. That's what it is.